Heat and changes of state. Okay, so here's some more vocabulary for you. So heat of fusion, which is the heat absorbed by a substance in melting from a solid to a liquid at constant temperature. Heat of solidification, which is the heat lost when a liquid changes from a liquid to a solid at a constant temperature. Heat of vaporization is the heat absorbed by a substance in vaporizing the liquid to a gas at constant temperature. And heat of condensation is the heat lost when a gas changes to a liquid at a constant temperature. Now, take a look. You have heat absorbed, heat lost. Heat absorbed, heat lost. Okay? Absorbed means endo. Lost means exo. Endo meaning endothermic, exo meaning exothermic. So heat of fusion is an endothermic reaction. Heat of solidification is an exothermic reaction. Now, we know that energy is conserved in all physical and chemical changes. So therefore, basically, the heat of fusion is going to be the same, but in just magnitude's the same, but the sign is going to be different. It's going to be opposite charge. So the heat of fusion is the same in magnitude as the heat of solidification, except heat of solidification is exo, and this is endo, meaning it's absorbing energy. Again, with heat of vaporization, that's an endothermic reaction, and heat of condensation is an exothermic reaction, but they are the same in magnitude, just opposite in sign. Alright, so when we're talking about water, the changes of state for water, the heat of fusion is 80 calories. Again, solidification is the same in magnitude, but just opposite, it's negative. Okay, so which means it's exothermic. Heat of vaporization is 540 calories per gram, and condensation again is negative 540 calories per gram. So take a look at these two differences. It doesn't take a lot of energy to melt a piece of ice. It takes a lot of energy to take that water and turn it into a gas. Okay, which is the reason why it takes a long time to boil water, because of this vapor, heat of vaporization. Okay? Alright, again, just reiterating the fact that melting and vaporization are endothermic, they require energy. Solidification and condensation are exothermic, they give off energy. Alright, so taking a look here, we have a solid, okay, going to a liquid, and it stays the same temperature up until all that ice has been melted off. Once all that ice has been melted off, then it starts to rise in temperature again until it reaches 100 degrees. Then it starts to boil, boiling water. It'll boil up until, and it's still the same temperature at 100 degrees, until all that water has been boiled off. Then if you apply more energy, it'll continue to raise in temperature. This is just basically saying the same thing. Okay, it doesn't take a lot of time, in other words, for ice to melt, okay, which means it doesn't take a lot of energy for it to turn from solid ice to liquid ice, okay, but it takes a long time for boiling water to boil and become vapor or steam. Okay, as you can see here, the temperature still remains the same even if there's a small minuscule amount of ice. Okay, it'll still remain zero until all the ice has been melted. Once it's all been melted, then it starts increasing in temperature. Same with boiling water. Boiling water will still remain at 100 until all the water has been boiled off, and then it will start increasing in temperature. Okay? Alright, now, each one of these requires some energy. Okay? So, The specific heat of ice takes only half a calorie per gram degree Celsius. Water takes 1 calorie per gram degree Celsius, and steam specific heat is 0.4 calories per gram degree Celsius, okay, which is the reason why, again, liquid water takes a long time to boil, because this is a lot higher. It doesn't take that long for ice to melt because of the fact that these two specific heats are different, okay? Alright, so in order to, basically what we're going to be doing here is we're going to be taking this graph and figuring out if we're starting at some point, say like solid water, okay, how much energy are we going to use in order to convert it to steam, for example. In order to calculate the heat required, we must use the specific heat capacity of water in its different states, okay, and the heat required for the change of state. Alright. So here's a sample problem. It says how much heat is required to change 25 grams of solid water from negative 20 degrees gaseous water to 140 degrees Celsius. Okay, now here is all of my equations that I need. Okay, in order to go from a solid to liquid water, okay, I need 0.5 calories per gram degree Celsius. Okay, the heat of fusion takes 80 calories per gram times the mass. Once I'm in the liquid, I need to figure out how much energy it is to raise by the degree of Celsius. Vaporization, 540 calories per mass per gram times the mass, and gas is 0.4 calories per gram degree Celsius times the mass. Now obviously in this stage, in this stage, and in this stage we have delta T's, okay, because it can be at different temperatures. Okay, we know that solid water is anything below 0 degrees Celsius, but it could be negative 20, it could be negative 30, so on and so forth. Liquid, it could be 20 degrees, it could be 50 degrees, it's still water. And gas is anything above 100 degrees Celsius. Okay? So we're going to take this information and apply. Here we are on our heating curve. Okay? And we start off at negative 20 degrees Celsius and we want to end up at 140 degrees Celsius. Okay, so we're down here at negative 20 degrees Celsius. We're going to be up here at 140 degrees Celsius. We want to know how much energy will it take to go from this point to this point, plus 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 all the way up here. Okay, that's going to tell us how much energy will be needed in order to heat up this negative 20 degrees Celsius piece of ice all the way to 140 degrees Celsius. This is how we do it. Okay? We know at this point we are at 100 degrees Celsius. We know at this point we're at 0 degrees Celsius. So what you have to do is you have to separate each piece. So from this point to here, that's 1. This point to here is 2. This point to this point is 3. This point to this point is 4. This point to this point is 5. And I'm going to basically add up those numbers. 1 plus 2 plus 3 plus 4 plus 5, okay, to get my answer. Okay? Now in order to go from here to here, I need my formula Q equals Cm delta T. In order to go from this point to this point, I use Q equals C m delta t. In order to go from this point to this point, I'm going Q equals C m delta t. Now, one thing that I need to keep in mind is my C's at the various states of matter. Okay, the C's are going to change. Okay? Now, in order to go from this point to this point, it's just Q equals heat of fusion times the mass. Okay? In order to go from, and that makes sense because at this point to this point, we don't have a temperature change. So we don't have a delta T. Same thing up here. We're going to take Q, and that equals heat of vaporization times the mass again. Okay? So let's take a look at how this all works out. So, in order to go from solid to another solid at 0 degrees Celsius, it takes us 250 calories. Okay, how did I get there? Well, I took 0.5 calories per gram degree Celsius, which is the specific heat of ice, times 25, which we get right here, and times 20 degrees Celsius. That is T final, which is 0, minus 20 degrees Celsius. Okay, T final minus T initial. Okay? Heat of fusion, where we take this right here, which is from our chart, times the mass, and we get another 2,000. Heat of liquid, we take our specific heat again, times the mass, times 100, and that comes from going from 100 degrees Celsius minus 0 degrees Celsius. Okay? We get 2,500 calories. Heat of vaporization, again, we're now on the plateau where we have 540 times 25, 13,000 calories. It takes a lot of energy. And gas, where we have 0.4 calories per gram degree Celsius. Again, that's the specific heat times the mass, times 40, which is T final, 140 degrees Celsius minus 100 degrees Celsius. Okay? So we take a look at all that, we add them all up, and we get 18,650 calories, or 18.65 kcals, in order to go from this temperature to this temperature. Now, you might be saying, wow, this is a lot of work, and this is something I really have to remember. You don't have to remember that. I will give you all these formulas. Okay? I will give you all these formulas. Okay? You just need to know how to apply it. Okay? By basically taking a look at this curve and not memorizing it, but knowing, like, you know, the different ways of solving the problem by plugging in all the different types of numbers, so on and so forth. Okay? All right.